Okay, so good morning, everyone, and welcome to this colloquium, the colloquium of the week, which is on a Tuesday instead of a Thursday, but it's still the colloquium. Today's speaker is Professor Peter Jonker, who I personally met when I was doing my PhD in the Netherlands, and then as a postdoc. He obtained his PhD at the University of Amsterdam in 2001, then moved as a Marie Curie Fellow to the Institute of Astronomy, Cambridge, and later as a Chandra Fellow to the Harvard-Smithsonian CFA. Then he returned to the Netherlands as a Benny PD Fellow, and finally got a permanent position at ESRON, the Netherlands Institute for Space Research. Since 2017, he has been a professor at the University of Radboud, and actually first by special appointment and then become a full professor in 2020. And in 2024, he became the deputy scientific director of NOVA, which is the Netherlands Association of Astronomy. So that's all on, well, the main highlights of his CV, but his actually scientific interests are actually energetic, high energy transients. And he has studied from X-ray binaries to tidal disruption events, including intermediate mass black holes, which he actually obtained an ERC consolidator grant in 2014 in order to study them. And finally, actually today he will be talking to us about a new type of transients, which are fast X-ray transients of FXTs, which he got an ERC consolidator, advanced grant in 2023 in order to study. And with all of this introduction, I will leave now the mic to him. So the floor is yours.
Thank you very much, Daniel. It's a pleasure to be here. And I realized this morning that my first steps as an observer, as an optical observer, were together with Jorge Casares here, very, very long time ago. So it's a pleasure to be here. As you can see from the list of collaborators, many are in this institute. There's also 2 PhD students that are in the audience. And this talk is also on behalf of Einstein Probe, which is a new X-ray satellite, a Chinese satellite with a ESA contribution. And I'm one of the ESA selected members of this consortium. So the talk is about fast X-ray transients. And if I can get to, well, yes. So first, I always like to start the talk with why. What are the scientific reasons for studying a certain type of objects? And here you see a list of 4 reasons for me, and there's a 5th reason because I find these interesting, intriguing objects. But that's a very personal reason, obviously. And maybe at this point in time, this list of 4 reasons doesn't say anything to you, and also how they are related to fast X-ray transients may not be very clear. But the goal is that at the end of the talk, you will realize how that comes about. I don't suspect you know very much about fast X-ray transients, so I first will dive into a little bit of what they are before showing how we can do this. So here you see the light curve of what I think is the first extra-galactic fast X-ray transients. So this is an important aspect. They are extra-galactic. Very large distances. You see a light curve in X-rays. First of all, seemingly nothing was detected, and then a very bright spike. And in this particular case, the transient light continued until the end of the observation. This was the Chandra discovery, serendipitous. So by chance, I looked at the Chandra data about 13 years later. I went through the archive to search for these kind of events. Now, after more than a decade, we can actually start to solve the problem of what these fast X-ray transients are. And the reason is that now in 2024, in January last year, this satellite was launched, Einstein Probe. It has 12 large field cameras and 2 nearly identical follow-up X-ray telescopes, also abbreviated as FXTs, very annoyingly. But with these 12 large field of view cameras, the Einstein Probe covers more or less 1/10 of the sky, and now I'm being positive. So it's about 3,600 square degrees of the sky instantaneously. That's a very large area, And it's doing this in the soft X-rays between 0.5 and 4 keV. This has never been done. So far, in X-rays, people used scanning satellites, so they don't have a very large instantaneous field of view. And there have been satellites that have coded masks that have a large field of view, but they're not so sensitive because they're coded masks, and this is a focused instrument. So new technology allows to focus the X-rays, and that way you get rid of a lot of the background, so you're much more sensitive. So the predictions were that we would find about 20 of these FXTs a year. Actually, the first year we already found 100, which is a bit overwhelming, I have to say. So here you see a sample of light curves from these large field of view detectors. So you see 9 fast X-ray transients. These are light curves, as I said. And you see there's kind of, if you look through your eyebrows, there's kind of 2 eyelashes. There's kind of 2 kinds of transients, ones that have a plateau initially and then a steep decay, and ones that flare a lot. And you have to see that these are log-log plots on the both y and x-axis are log-log. And another point to note is that the durations of these transients are typically hundreds to, in some cases, thousands of seconds. So they're quite long still for fast X-ray transients. They're much longer than typical gamma ray bursts, but they obviously are detected in gamma rays. So why is this Einstein probe so important? It can detect a lot of them, but what it also can do, and that's crucial in this field, is that it alerts us very rapidly about the existence of this transient. So what you see in the top panel is the number of FXTs that have been discovered with Chandra, and then the amount of, Chandra and XMM on the right here. And these are the predictions for Einstein probe. And you see that on the x-axis is the time between discovery and the announcement, or us astronomers becoming aware of it. In the case of Chandra, that has been a year or more. Why is it a year or more? Because we can only find it in archival data. Obviously, we can find it if we are allowed to search through everyone's proprietary data, which we're not allowed to do. And as an individual observer or someone who's using Chandra, it's hardly any point to go through and say, oh, maybe I have a fast X-ray transient in my data, because the rate for Chandra is about 1 per year. So if you have a Chandra observation, no one bothers to look because the chance is very small that it's actually something in your data. But Einstein probe finds these things and alerts us within 15 minutes is the goal. And they don't always get to 15 minutes, especially in the first year of operations. They had to start up, they had to commission the satellite, but they're getting there. And so this enormous factor of 10 to the 4 increase or decrease in latency and the time between detecting it and telling the world of astronomers about it, that helps us, and that's what you see in the bottom panel. Here you see absolute magnitude, also as a function of time. And this 10 to the 4 in time allows us to find these things in optical when they're still very bright. So the light curves that you see are for different kinds of transients. And you see, if you wait a year, most of the optical light has been gone away. So for all the Chandra discovered FXTs, fast X-ray transients, we've never found an optical counterpart or a radio counterpart or anything else. So we can't localize it perfectly well, even though the Chandra localization is half an arc second sometimes, or an arc second if it's far off axis. You can't localize it that well. You can't study an optical counterpart. And there's a lot of information in the optical, I think many of you know. So some statistics about the first year of Einstein probe. We found about 100. 27 turned out to have a burst of gamma rays associated with it. And our group's Mary Ravasio, she's a postdoc in our group, and she is, we have a deal with Fermi GBM that she is looking very rapidly in these Fermi GBM data to find these gamma ray signals if they are there. So 27 have a gamma ray burst associated with it. So these X-rays are associated, in some cases, with a gamma ray burst. We found optical counterparts. For some, we have no optical counterpart, 40% or something. 22 have redshifts, and of those, 60 come from our group. And in the figure that you see that the top row of light yellow bluish, light magenta blue dots, You see that the fast X-ray transients that we find with Einstein Probe are higher luminosity than the ones that we found with Chandra. And that is interesting and intriguing. So there seems to be two populations. The redshift distribution is at the moment still similar. So what are the models for these things? One of the models is that they are regular supernova shock breakouts. And here, if the movie goes along, you see an animation of a supernova shock breakout. So this is a core collapse supernova where the actual explosion of the supernova comes because of the shock breaking out of the surface. If you have a massive star that is not too large, so not a red supergiant, but say a Wolf-Rayet star, then, or very stripped envelope massive star, then this X-ray signal, this breakout signal can be detected in the X-rays. But it's a rather soft X-ray signal, and it's rather faint in terms of the peak luminosity that you expect is 10 to the 44 ergs per second at most. And this comes from 1D modeling. And it turns out that if you look at some 3D models that have been done for red supergiants, it looks like the peak luminosity goes down. The total energy is preserved, but the peak luminosity goes down. The amount of energy is just spread over a longer period of breakout. So we don't expect to find many of these regular supernova breakouts because they're not so luminous. And so far in the first year, we have no single clear normal supernova shock breakout. Other models that we do consider, and I put these numerals here because throughout the talk, I will come back to these. You see one of these numerals that you can remember what the topic is. So some are related to gamma ray bursts. So that's the first kind of. As we know, for 27%, more or less, 30%, they have a gamma ray signal. So, but can they be also off-axis gamma ray burst? So we don't see the gamma ray signal directly, but maybe we see X-rays because we're not in the beam. Turns out that is very difficult. So that's why the small no. It turns out that some of these Einstein Probe fast X-ray transients are associated with collapsars. So that's why there's a yes, several. Initially, we thought maybe white dwarf tidal disruption events by an intermediate mass black hole can be responsible for this signal as well. It turns out, if you look at the expected rates for intermediate mass black hole tidal disruption events, this can only be a few percent, although these numbers for these rates are very uncertain. And there's a strong theoretical groups have worked on binary neutron star mergers, and some of them might leave behind rapidly millisecond spin period, rapidly rotating magnetar. The spin down energy of that could power the fast X-ray transients. At the moment, we can't test it yet with EP, Einstein Probe detected FXTs. I'll come back to that, why that is. And there could be something completely different. And one of the models that came out rather recently is from Paradiso and Eric Coughlin et al. They said, well, if you have a failed supernova, so your shock isn't powerful enough to explode your star, so the shock stalls and gravity wins and the star collapses into a black hole, this falling of material through this stalled shock could give rise to a fast X-ray signal. So that is something that we are looking for as well and trying to test. So as I said, some are associated with gamma ray burst. Here you see a movie from simulations from Ore Gottlieb, and it shows the collapse and the formation of a black hole and mass falling onto this black hole, powering a very powerful jet. It plows its way through the remnants, through the envelope of this star. And if we're looking from the top, you see this excavated region and you see a very high Lorentz factor jet being pointed at us. Those are gamma ray bursts, those we can see. And indeed, one of the first FXTs found by Einstein Probe was together with a gamma ray burst. So this is a slightly complicated figure. You see time as and the count rate in X-rays in this line, and this reddish marked vertical position is when the gamma ray signal was discovered. So weirdly enough, the gamma rays were discovered after the X-rays. That's kind of new. It was seen, I think, once or twice before in Beposak's gamma ray burst. And that's learning us something about how the gamma ray burst originates. And these big crosses are the photon index in the X-rays if you fit the X-ray spectrum. So the first one was actually also at a quite high redshift. And you can use these high redshifts to study how the epoch of reionization, how the reionization came about. As gamma ray burst is not my primary field, I will not discuss or dwell a lot on gamma ray burst. I'll show some work that a master student or former master student, Hannah Wiegand, did in the guidance of Mary Ravasio to show that they are not off-axis gamma ray bursts, or it's very difficult to make a large fraction of these fast X-ray transients originate as off-axis gamma ray bursts. So here you see light curves of an afterglow. So what we did, we modeled 13 on-axis gamma ray bursts, where we had a lot of optical, radio, and X-ray data. So we modeled that the afterglow using afterglow pi, which is an established model for the afterglow, and then said, okay, now we know what the afterglow looks if we are on axis. What if we go off axis? And here in the color bar to the right side of this figure, you see how the off axis angle increases. And so it increases from yellow to dark blue, from 1 to about 8 degrees off axis. And what you see is that the light curve, the luminosity drops like crazy. The more off axis you go, it drops very rapidly by orders and orders of magnitude. What you also see is that the shape of the light curve changes. And you get this more peaked phase if you're far off axis. Peaked, shorter duration, and much lower luminosity. And it turns out this combination of light curve properties and peak luminosity and duration is very hard to reconcile with the observations of fast X-ray transients. This modeling, if you're an expert in this field, you may have noticed this was a uniform jet. We also did this for a structured jet, and similar conclusion. You cannot make most FXTs in this way. There's a little bit of overlap, as you see here. Is the duration on the x-axis, and this is the luminosity. All the red crosses are fast X-ray transients. All the yellow bullets are the models from off-axis afterglows. And you see, there's a little bit of overlap between a few of them. And so these and here, those could perhaps be due to off-axis afterglows. So we cannot rule out that any of these FXTs are due to off-axis observations of GRBs, but the large majority should not be. However, if you still consider a massive star, core collapse, black hole formation, it's not clear that in all cases the jet is powerful enough to actually plow all the way out. This might depend on the spin of the black hole that you form. If the spin is lower than close to maximum, the jet power is much lower. And what you then get is that the jet is choked, and then you get what's called a cocoon. And the cocoon can break out, and you don't see a strong gamma ray signal because the Lorentz factor is much lower than in the case of a real gamma ray burst jet. So the cocoon breakout, yeah, that could actually give rise to an X-ray signal and the optical follow-up. And this was found for the first time by Joyce van Dalen here in her paper. It was a FXT that was at a redshift of 0.4. It sits next to this large galaxy, which is also at 0.4, so they are associated physically. And if you study this object in detail, it turns out that some of the aspects are like luminous fast blue optical transients. And LF-bots, as we call them, is another group of transients found in optical, but have strong X-ray and radio detections as well, on longer timescales than typically these fast X-ray transients. So what you see here is the absolute magnitude at peak on the y-axis as a function of time, and this is the time above half maximum. And you can also have the rise time or similar metrics on the x-axis. So what you see is that these cow-like, because the prototypical LF-bot is called 18 cow, astronomical transient 2018 COW cow, and that started the field. There's about 10 known now, and here you see that they are really bright and fast compared to other supernova types. And so here you see the cow started this nomenclature that we then try to name them after mammals. So far, so good, except I think a few down here. This one, we clearly thought it MRF, that's Smurf, it must be Smurf, although I don't think a Smurf is a mammal. So they have unique characteristics. We don't know what they are caused by. Initially, people thought, okay, these are some kind of exploding star. However, there's no nickel found. In all the other core collapse supernovae, we find nickel decay. It's powering the supernova at later times. In these, we do not find nickel decay. That's odd for a massive star collapse. However, if you have a massive star fully collapsing and there's not much nickel produced, there's not much material outside the event horizon in the end of this black hole that you form. It is clear that the power source is not nickel decay, it's not radioactive decay at early times, also not at late times. So there is something powering this. It could be a magnetar, obviously, that has been spin down of a magnetar has also been proposed, or fallback accretion onto a black hole. And in some of these, at late time, there is very strong variability seen with GTC hypercam observations. So you see very rapid variability, very large amplitude variability in the optical at late times. So that is very odd for any supernova type. So people also thought maybe these are powered by a tidal disruption event. And the timescales are telling you then it has to be an intermediate mass black hole. So here you see work from two of my former PhD students. Here's Anne Inkenhaag's work, and this is Tsung Zhao's work. So on the y-axis on the left figure, you see absolute magnitude. So the cow was very bright initially, dropped like crazy. But then in the UV, it stayed bright. It hardly decayed. And now we have a fifth observation and still doesn't decay. Not so much. And the red and the blue that you see, those light curves, are models for a tidal disruption event accretion disk around a massive black hole. And the mass is then more or less the free parameter. And what you get is a few hundred solar mass black holes. And then we were very surprised that if you model the initial X-rays, so that is during this phase, really early on, was a very bright X-ray source. If you model that X-ray emission as a slim disk, which is a very thick accretion disk, because the mass accretion rate is so high, your standard Shakura-Sunyara thin disk model doesn't work, it's not applicable there. But if you model this with a slim disk, then you can get the black hole spin and the black hole mass out. It's completely independent from this late-time UV observations and modeling, and you get very similar masses, a few hundred solar masses. So could this be a very massive star collapsing into a few hundred solar mass or 100 solar mass black hole, then accretion onto it, powering these transients? That's one of the models that we're now considering. So back to a fast X-ray transient, because for those LF pods, we've never seen a fast X-ray transient signal. Also, maybe we're not looking in the right direction at that point in time. And before Einstein Probe, we couldn't even look at it. The chance that Chandra or XMM is pointing at something where there is an LF pod is 0, because the field of views are too small. So back to this fast X-ray transient. Here you see the light curve in optical. It has more or less 3 peaks. The initial peak, a second peak that is really bright, and then at late times there is a peak, and when it is exactly peaking depends on which band you're looking at. But at late times, observations in spectroscopy, which is indicated, the epochs are indicated by these vertical dashed lines. At late times, we see a clear type 1c broadline supernova. So that the third peak is powered by that. And if you plot those 3 peaks on this absolute magnitude duration diagram, then you see that indeed it's really in this range where you find luminous fast blue optical transients. It's not a prototypical LF pod because it's not as blue initially. It's also not thermal. LF pods are thermal emission. This is a Powell law. It's very blue initially, but it's not thermal. But it's in the same range. Another EP transient from this year, January the 8th, also resides in this area. And you see here that at later times, it falls in this area where you find 1C broadline supernovae. So if you model this with, in this particular case, it was modeled with the package Redback, you see that you can model this really well with three components. You have the initial shock cocoon breaking out, that is the dashed line. Then you see the dotted line, this breaking out of the shock explodes a star, and that interacts with any material that is still around the star from previous mass loss. So this shock interaction is what you see in this dotted line. And then in the dashed line, you see the supernova peaking at late times. Those three components together can explain the light curve and the spectroscopy that we see really well. There is something weird with this source, that all collapsars, so these are associated with long gamma ray burst and the collapse of a massive star, are always in the brightest UV spot of a galaxy. They're not in a very massive spiral typically, and also not very far out of a spiral. So we went back to this location and took very deep observations with GTC, hypercam, and here you see there is a hint of a smudge of a detection of extended object. We do not know the redshift is the 26 magnitude in G-band, so we don't take a spectrum. But if it's at the same direction, at the same distance, at the same redshift, then the absolute magnitude is minus 15.6. So the question is it really associated with this bright galaxy? Then that galaxy has a very high brightness, so very high luminosity. And here on the x-axis, you see the normalized offset and as a function of the absolute magnitude of the host for different kinds of transients. So where in the hosts are all these transients? And you see if it's outside this host, it's a very peculiar location for a massive star exploding. If instead it is in this smudge of, if that is a dwarf galaxy, like it's really faint, it's fainter than NMC, it's SMC type, maybe a bit fainter than that, then it's also still a very peculiar location for these massive star explosions, but it fits the bill much better. Now, the question arises, or people have been telling me, all of these FXTs, they're just gamma ray bursts where either off-axis or they're low luminosity gamma ray bursts, and then the Amati relation tells you most of the gamma rays are no longer gamma rays, but they shift down for low luminosity gamma ray bursts to the X-rays. And so they say they're all collapsars. And we have for three now, we have good evidence, very solid evidence, I would say, yes, they're collapsars because we've seen the type 1c broadline supernova. So three are clearly type 1c broadline supernova associated with them. They are collapsars. No gamma rays detected, but that can be explained by the fact that they are low luminosity gamma rays. Some of them are not low luminosity in total. This one is the 0414A. It's really high luminosity, above 10 to the 48. But for gamma ray bursts, this is low luminosity. So this is what I'm plotting here, is the Amati relation. So you see the peak energy in X-rays or gamma rays, if it is a lot of keV, as a function of isotropic energy. And the isotropic energy is if you assume that the jet energy that you see is actually all over. So it's it's an overestimate. But then you get these two populations. Type 1 GRBs are short gamma ray bursts, the typical compact object merger gamma ray bursts, double neutron star mergers, for instance. And the type 2 are the collapsar gamma ray bursts associated with massive star collapse. And you see that at least one now, this is a source where here's the name, the telephone number, and discovered the 13th of November last year, that doesn't follow the Amati relation. So it's likely that it's not exactly a collapsar. There's ways around it, but not all of them are typical collapsars associated with long GRBs. We have older events where we know for sure that there was no supernova associated. We have very deep limits at the time where you expect a supernova. We know the redshift. It's not associated with a collapsar. It could be associated with those binary mergers, binary compact object mergers. But not all of them are collapsars. So let's go to model 2. A small fraction could be intermediate mass black holes disrupting a white dwarf. And you see a simulation from Stefan Roswok. And if you want to know more about this, we wrote a paper, a review paper with Kate McGuire as first author. And the simulation will run so you disrupt a star, in this particular case a white dwarf. I'll show in the next slide why that can then only be done by an intermediate mass black hole. What you see is if you disrupt the star, that's all fine and nice, but you still have to accrete this material in order to get light out of it. Accretion is the process that drives the emission. And it takes a while. And in this particular case, you have to shock this emission. You have to get rid of angular momentum. Like in many accretion flows, angular momentum has to be transported out. Material can then fall in. In this particular case, the idea is that in TDEs, tidal disruption events, the shocks here, and there's a nozzle shock here, that gets rid of angular momentum that allows you to accrete material. While I'm speaking, real time in this simulation has also been running. It's of the order of a few minutes. So that has the right time scale. So this is a 1,000 solar mass black hole disrupting a 0.2 solar mass white dwarf. And that's why these time scales are essential to explain something like a few hundred, 1,000 second flare in X-rays. So that's why we need intermediate mass black holes disrupting white dwarfs. If you were to disrupt a massive or a main sequence star, you're much further away from the black hole because that main sequence star is much less compact than a white dwarf. So it will be destroyed much further away. So the timescales go up for these events. So those cannot explain the fast X-ray transients. So why do I need an intermediate mass black hole? On the x-axis, you see black hole masses. It runs from 10 to the 3 to all the way 10 to the 9. And here you see radius, so distance from that black hole. So assume you're a star, you're coming from far above, where's my pointer, and you go closer, and then at some point you're so close to the black hole that the tidal forces, which is the difference in gravity between the top and the bottom of a star, gravity exerted by the black hole, so that tidal force is stronger than self-gravity of the star, you will tidally disrupt your star. So if you come from far away, you get closer, then there's a competition. Either the star is disrupted or the star crosses the event horizon. And whatever happens after that, we do not see anything of it. So for 10 to the 6 black hole, here, if you're 100 solar mass 10 solar mass main sequence star, you will be disrupted by this 10 to the 6 solar mass black hole. If you're one solar mass main sequence, you will be disrupted. But if you're a white dwarf, no, you will cross the event horizon, which is depicted by these diagonal dashed lines. That's the location of the event horizon as a function of black hole spin. So the event horizon shrinks when the black hole spins faster and faster. So the top one is for 0 spin, this is for 0.9 spin, and this is for spin of 1, the maximum spin. So if you're a white dwarf, like a 0.3 helium white dwarf, 0.3 solar mass, you might just be disrupted outside the event horizon of a 1,000,000 solar mass black hole if that black hole is maximally spinning. But any other more massive white dwarf, you will not disrupt outside the event horizon because the star has crossed the event horizon before the tidal forces are too strong to disrupt it. So if you see a massive white dwarf being disrupted, you know it has to be an intermediate mass black hole because otherwise it would have swallowed the star whole. And finding intermediate mass black holes is is becoming more and more pressing because James Webb is finding these supermassive black holes at very high redshifts, larger than 10. That means that the universe was a few 100 million years old. And how do you grow a very massive black hole, 10 to the 9, 10 to the 7, 10 to the 8 solar mass black holes? How do you grow them out of very small density fluctuations in a few 100 million years? Here you see two ways. If you have direct collapse of a massive gas cloud, 10 to the 5 solar mass, 10 to the 4, you form not so many black hole seeds of 10 to the 4, 10 to the 5. That's good, because then you don't have to grow that much. You only have to grow a factor of, say, 1,000,000 to 100,000 to become a supermassive black hole. But if instead you form seed black holes out of population 3 stars collapsing, then they're about 100 solar mass, we think. And then you have to grow them very rapidly, and that is a problem. So we'd like to have these intermediate mass black holes to grow some supermassive black holes very rapidly early in the universe. But the evidence for the presence of intermediate mass black holes is very scant. It's not solid. And we need dynamical evidence, a solid proof. I don't have to explain that to many of you here. You need dynamical evidence for the existence of a black hole. There are some observations, like recently there was an observation of omega Cen proper motions of stars around it, showing, oh, there's a few thousand solar mass black holes. And as soon as that hits the archive, another paper was written saying, well, you can also have this if you have a lot of stellar mass black holes floating around. And that's very difficult to disentangle the two options. So very solid evidence for intermediate mass black holes is still very difficult to get. Einstein Probe is also playing a strong role here because it's finding tidal disruption events, not white dwarf tidal disruption events, but it's finding X-ray signals much longer than the fast X-ray transient. And in this particular case, there is a host here. They saw the redshift of the transient. They see the host. They know it's at the same redshift as this host galaxy. So this is an ultra-compact dwarf where there is a massive black hole disrupting a normal main sequence star. But it's an intermediate mass black hole. So these are also good indications, but there's always some uncertainty about the mass of that black hole. Whereas if it's a white dwarf that you see tidally disrupted, no, it's just geometry and gravity that tells you it has to be an intermediate mass black hole. So this is the same light curve that I showed you as the second slide. Now, however, the y-axis is log and the data is binned. So what you see is that there are two precursors here. There were 16 and 11 Chandra photons detected, and very significant detections with Chandra because the background is so low. And so there's two precursors to this main flare, and it's about 4,000 seconds separation. And this 4,000 seconds sounds really like the orbit of a white dwarf around an intermediate mass black hole. It's that order of time scale. And then gravitational wave radiation shrinks that orbit, and at some point it's way too close. So you chip off some mass, chip off a little bit more mass. That gives rise to these initial peaks, maybe. And then at later times, and because the orbit shrinks a little bit due to gravitational wave radiation, the whole star is disrupted and you get this main flare. And you have a lot of accretion flow onto this black hole later. So that is one of the models for the explanation of this fast X-ray transient. This source lies in the outskirts of M86. So initially we thought, okay, here you have a small galaxy that is falling into M86. A tidal stream of stars is stripped of that galaxy, and the dashed lines are just to indicate this stream. The red circle is the location of this transient. So we thought, okay, it's bound to be associated with M86, with this stream. But if you look very deeply with GTC Hypercam, you see that there's an extended object just associated with this error circle. It doesn't come out very well, but it's really an extended object. So there is a galaxy there. Unfortunately, we don't have this flash of optical light because it's already faded away by the time that we found this X-ray transient. If you take size luminosity relations for galaxies, in this particular case it's for dwarf galaxies, you see that if this source is, pointer is dying, if the source is at M86, it has a half-life radius of this, and the absolute magnitude would be really faint. It can be a really faint dwarf galaxy. There's also a group of galaxies that reside at a larger redshift, it turns out. And if you place it at that redshift, it could also still be a much brighter dwarf galaxy. So yeah, you have to look at the hosts in cases where you don't find the optical flash, the afterglow, the counterpart. So you have to look at the host, and Agnes is doing that. What is interesting with Einstein Probe is that if we see a white dwarf being tidally disrupted, a fraction of those white dwarfs will detonate as a peculiar type 1a supernova. And the reason is that while you stretch a star in one direction, you compress it in two other directions. So the central density will go up. So in some white dwarfs that are closer to the Chandrasekhar mass, the central density will go up, and that will make it to detonate. It's not at the Chandrasekhar mass, so it will have a lower peak luminosity than typical 1As. And that's what you see in this plot here. You see the absolute magnitude in different filters as a function of time. But what you see is that in, say, the redder bands, you can have something that is of order -17 at peak. And absolute magnitude of a normal 1A go up to above -20, so they're much brighter. But we hope to find this, and if we do, we can take spectra, hopefully, if they're nearby enough, and then you can see that the spectra, they evolve from blue spectra initially to red spectra at late times, and they have the typical type 1A supernova features in them. And the evolution has a typical timescale of the order of a month. So far, we haven't seen any of these. But this is a signal that we look for. Finally, and I'm seeing I'm running out of time, so I go quickly. This model that if you merge two neutron stars, the merger product can be a light black hole, then they can't power a fast X-ray transient. But if the merger product is a millisecond magnetar, and the spin down energy, for which you see the formula here, that can power the X-ray signal. And it depends what you see, depends on our viewing angle. So here, if you're viewing from the top, it's like a low luminosity, it's like a short gamma ray burst. You see the jet. If you are looking from what's called the free zone, you see this magnetar X-ray signal, magnetar powered, and you see this plateau decay. And we've seen many of these. If, however, you're looking through the equatorial plane, you have to look through this kilonova ejecta. This is this R-process material that has very high complexities. So that means that the optical radiation, X-ray radiation, doesn't come out until that material is fully ionized. So it takes a while. You don't see X-rays initially, and then you very rapidly you see probably most of the decay or a very short plateau phase. We've seen some of these light curves. They're like that. You can fit them. You can model the parameters of the magnetar, and they're typical magnetar parameters that you expect also in short gamma ray bursts. However, the proof is to find the kilonova, because then we know, yes, there was R-process elements. Yes, there were two neutron stars that were merging. We haven't seen the kilonova except in 1708-17, the gravitational wave discovered event. And this magnetar spin down alters the kilonova. What it does, it injects energy into this kilonova signal. So it becomes brighter. So here you see 3 kinds. The dotted lines are for different filters in the optical and near infrared, different filters for normal kilonova, the models that we have for those. Then, depending on the amount of material that you eject in this kilonova, then you have this either dashed or full lines. So the magnetar is enhancing the amount of energy, so the total integrated flux is higher, the fluence is higher, but it also, in some cases, speeds up the signal. So you have a faster, brighter, faster decaying optical transient and infrared transient. So far, none of this has been seen, and there are good reasons for this, because here you see the apparent magnitude of all our follow-ups, and the triangles are the upper limits, and the dotted are detections for EP discovered fast X-ray transients as a function of time after trigger. And what you see is that this really quickly fast response, we haven't been able to do it yet because Einstein Probe has not told us about the discovery rapidly enough in many cases. They're improving on this by having 24/7 people on duty, by having faster downlinks from the satellite. So they are filling this parameter space in time, and we have to respond by very deep observations, because then we can find these kilonova enhanced, so the magnetar enhanced kilonova signals. We have one case that is in this direction already. Within 5 hours, we have very deep Gemini observations. Unfortunately, due to a failure of the instrumentation, we have no infrared observations, but we have 2 epochs very rapidly. Epoch 1 within 5 hours. You see the localization uncertainty from the X-rays. Swift is following up all of these now automatically. It's a priority 0 set for Swift. But there were no optical transient was discovered in this particular case. So these are called dark FXTs after dark GRBs. And some dark GRBs are dark because of extinction. In this particular case, we know it's not due to extinction, because that would also kill the X-ray signal. So unlike gamma ray bursts, the gamma ray signals would go through extinction like like that, and not be hampered by this. But the X-rays are hampered. So for fast X-ray transients, we do not have dark FXTs due to extinction. We can have dark FXTs due to very high redshift. If all the optical emission is just shifted out of the optical band by very high redshift, so then everything is in the near infrared or further. But this particular source is a dark FXT. So this brings me to my conclusions. So there's several models. We know that a few of these are due to collapsars. We are starting to probe these very fast responses. So maybe we can find the kilonova enhanced, so the magnetar enhanced kilonova associated with double neutron star mergers. It's a bit overwhelming how many FXTs Einstein Probe is finding. And if we can prove, so now I'm coming back to the second slide of why are you interested in this? If we can prove that some of these are due to binary neutron star mergers, we can get the redshift through the optical observations. You can localize these events very rapidly due to X-rays. So gravitational wave detections in the next generations, Einstein telescope, not Einstein Probe, Cosmic Explorer, they will find these gravitational wave mergers, binary compact neutron star mergers, to very high redshifts. How do you find the optical counterpart? Well, if you first localize them to a few arc seconds by looking in X-rays, then you can point a very big telescope at that location and say, ah, yeah, now I see something varying in optical or infrared as well. So this intermediate step of X-rays is going to be important, I think. And for that, we need Theseus. So if you're in an ESA committee, please select Theseus as M7. And then we can actually take a spectrum in the optical, get a redshift. From gravitational wave detections, you get a distance. So you have a relation between redshift and distance, and that's h0 in between there. So you can measure how h0, if it's a constant or if it varies as a function of time. So these are the outlooks to the future. Thank you very much for your attention.
Thank you very much, Peter, for this really nice talk. Do we have any questions first from the audience here? Or online as well? Actually, I do have a question. So as we have seen in your presentation, you have a lot of different possible origins for FXTs. So it seems that the way to go now is that there are different populations creating the same type of signals. What kind of instrumentation or satellites are you hoping for in order to be able to test some of these models?
Yeah, so it's clear that there are different populations. Some are collapsars, some are clearly not due to a collapsar, so not a massive star collapsing, because we know that we haven't found a supernova. It could be a collapsar leaving no supernova behind. That would be a direct collapse for a black hole. That would be interesting to find those massive black holes as well. So what do we need? We need very fast responses of telescopes. And first we need fast announcements from Einstein Probe. They have gone down to 7 minutes. It's the record now. So that they find something and within 7 minutes they tell us there is something. So that's already getting there. But we need the 7 or 15 minutes for all of them and not just for a very small sample. And then we need to have telescopes all over the world that can respond, because sometimes it's still daylight here on La Palma, and then we're waiting for a couple of hours until the night starts, but the optical signal might die away already. So we need telescopes all over the world to be able to respond very rapidly. And we're setting this up, and we have this more or less at the moment. But we don't have these very fast responses or announcements for transients so far. Regularly, we have it occasionally. And in the further future, so Einstein Probe is approved for at least 5 years, well, 3 + 2, and we're already in the 2nd year. So hopefully the Chinese will extend the mission. That is depends on money, and even in China, that's not infinite, I was told. And then after that, yeah, if we lose Einstein Probe at some point, we need something similar, and Theseus is the follow-up, and Theseus will go beyond what Einstein Probe is doing. But that will be 2036 or so, if it's selected and then launched. So.
Thank you.
have you considered using polarimetry observations
Yes.
in order to disentangle some of these?
Yeah, at the moment, so polarimetry would be fantastic. Through Stargate, and our group on the VLT, we work together with Stargate. We are all member of Stargate, more or less. There are polarimetric observations planned, but you need a very bright afterglow, no, quick enough. And we haven't had one of those yet. So would be fantastic, but you need a very bright signal in order to be able to do it. Yeah, no, yeah, that's an underutilized tool to measure the geometry of the emission. Yes, great if there are TOO observations, say at GTC, that allow us to take polarimetric observations.
Thank you very much for the talk. How do you interpret that we don't detect the high fluxes at lower redshift? We know that we have a lot of supernovae from ZTF, for example. So how do you connect the two?
Yeah, so what I think why we do not detect shock breakout for like normal explosions of supernovae in X-rays, the peak luminosity that you expect is 10 to the 44, but that comes ergs per second, but that comes from 1D modeling. And I think that if you go to 3D modeling, if what was seen for red supergiants, where you do not expect an X-ray signal, but you expect an optical UV signal at the breakout because the star is so large, and the velocity when it breaks out is much lower than in a, say, Wolf-Rayet breakout. You do not get X-rays at the high peak luminosity that we seem to expect or seem to find in 1D models. They do exist, we know, because there's a supernova 2008D that was discovered by accident. The Fast X-ray Transient signal was discovered when Swift was observing another supernova in the same galaxy. Something went off, and it found the Fast X-ray Transient. Swift found it, and it was shown that this is a stripped envelope supernova that went off. So you have, but the peak luminosity was 10 to the 43 ergs in that particular case. So we know that they should exist in the X-rays, but it's only some core collapse supernovae that produce this X-ray signal. Most of them produce a UV signal that any extinction will kill. So my thinking is that well, obviously Einstein Probe only covers 10% of the sky. So if something happens there and Einstein Probe is looking there, we're not finding it. So at the moment, it's still okay by chance that we haven't found them. Because the distance out to which Einstein Probe can find them is not so large, because the peak luminosity is so low compared to these other signals. Yeah.
Thank you.
Okay, I think we have a raise hand online.
Yeah. Hello, Almudena Prieto. Thank you very much for your talk. I have a question about the supermassive black holes and the detection of these events, because one of the ideas that have been associated to many of the supermassive black holes that we have, particularly in the near universe, is that they accrete very, very low. They are very, very sub-Eddington. And so this little accretion has sometimes associated to the event or interaction with a star that gets in the event horizon, or maybe get close and get disrupted, because the large majority of these supermassive black holes in early type galaxies are such as sub-Eddington. One example, for example, is our own Milky Way. There must be, what you think, there should not be more detections associated to this type of galaxies. I know the problem is that the difficulty to detect it, but it should be more.
Yeah, so the supermassive black holes at very low accretion, we do not think that they are associated with these fast X-ray transients, but indeed there are models that say that what is the source of this very low accretion rate in those cases? And that is that you have had tidal disruption events in the past. The estimates are, or calculations, that's if you look at 10 to the 4 galaxies in 1 year, you should find one tidal disruption event. So per galaxy, it should have a tidal disruption event every 10 to the 4 years. It turns out that these tidal disruption events, they stay, so the mass fallback rate can be very low at late times. So they could power this low luminosity AGNs that you're talking about, especially if you disrupt, say, red giants. So you don't fully disrupt a red giant, you only strip parts of the envelopes off. And and the red giant, if it's on an orbit of a couple of hundred years, every couple of hundred years, you strip a little bit of material off, and that is then accreted and powers this low luminosity supermassive black hole AGN. Is that what you're talking about?
Yes, I was thinking,
and I agree.
A large number of them. So it's the majority, by the way.
Yeah, it could be that this is the source of the mass accretion for the majority of them, yes.
But the detection on these galaxies must be a bit difficult, right?
Yeah, the detection rate of those very low luminosity AGNs, yeah, you can't go beyond that except in a local universe, indeed, because you need very deep observations in X-rays. And then you also need very high resolution because you start to probe luminosities that are so low that X-ray binaries can also obtain these luminosities. So you have to be able to pinpoint the source of X-rays to really the center of a galaxy. So
yeah,
it becomes very difficult. Yeah.
Yeah, that's the problem.
Yeah.
Okay.
Thank you. Any more questions? No? Okay. If not, let's thank the speaker again.
Thank you.
Thank you. Thank you.
For the students in the room, please come around with take note of your assistance.
More.